Hello pre-cal students. In this video we're going to talk about trig equations such as this one that we looked at in class, and I gave you 5 of them, so here they are, 1, 2, 3, 4, 5, and I gave you these hints, and I said in some arrangement these hints would apply to the equation. So let's just solve them all. So this one, most classes we got through this one, or up to the end of it. As you can see, we want to start by just isolating this part. So we would add the 1 and divide by 2. And so we would wind up with cosine 3t equals 1/2. And I started class by showing you that cosine of x equals 1/2 would generally, as an equation, have a solution set that is x is equal to pi over 3 and 5 pi over 3, because those are the two angles that natural solutions. In other words, between 0 and 2 pi on the unit circle, you've got this one with a cosine of 1/2 and this one with a cosine of 1/2. So these two values, onto these we would add our 2 pi n or 2 pi k, so that we would get the full list, right? All of the coterminal angles, so that we have the complete solution set. And we can write k as any integer. So I showed you that early in the class, and then you wound up here. And so I was just, what I was trying to get you to do is say, well, if cosine of x is 1/2 and cosine of 3t is 1/2, that means that we can say that 3t in this equation equals x in this equation, right? And so therefore 3t equals everything you see here. So how can I make that clear? 3t equals x, right? Because instead of 3t we could have x here, and we would write over to this equation. And if 3t equals x, then cosine of 3t equals 1/2, and 3t is going to equal all this. So we can say 3t equals the whole schmear. I guess I got to write it again. 5 pi over 3. One thing about this, it forces me to slow down. It's like writing with the mouse. Now, since the goal is to solve for t, right, all I got to do is get that by itself. That means that I want to divide by 3, and it turns out that this will work if I divide every term by 3, including this term with the k in it. So we wind up with t is equal to pi over 3 divided by 3 gives me pi over 9. And then I divide this by 3. Okay, and then the other part of that is 5/3 pi divided by 3 gives me 5/9 pi. And again, plus 2/3 pi k, where k is any integer. Okay? So this is the real solution to this equation. Okay, so that one was, which one was that? Divide by a coefficient is the last step. So we did that. In other words, the last thing we did, this coefficient right here, we saved it until the end, and then we divided everything by it. Okay, so moving on to this one. Here, what some people did was basically to divide out cotangent on both sides, leaving them with cosine squared x equals 2. Well, that's fine as far as getting you some of the solution set, but it's not going to get you all of the solution set, because anytime you divide out, this right here is an unknown. This right here that we divided out is something that's unknown because it includes the variable cotangent of x. If you divide out an unknown on both sides of an equation, you're probably dropping out some of the solution set. You're probably leaving some of it behind. And so what you wind up with, just from what's inside, just from this, what you're going to wind up with will be probably part of the solution set, but not the entire solution set. So we got to back up here, and we're going to use this piece of advice right here. Get a 0 on one side and factor. Okay, so watch how this plays out. If we subtract, lower thing here, if we subtract this term from both sides, then, now you might be tempted to try to combine these terms, but they are not like terms. So we'll just have to write them, both of them out completely. Cotangent x times cosine squared x minus 2 cotangent x equals 0. All right, so now my advice was to factor something out. So you see how we have the common factor here and here. I'm going to bring it out, cotangent of x, and since that's a factor of both, I can just write in here, right, so cotangent times this gives me this, cotangent times 1 gives me that. Oops, I made a mistake. You probably saw it. Here we are, minus 2. Cotangent times 2. It's a good thing I did that little checking move there. I always like to check as I go. Cotangent times 2 gives me 2 cotangent. Okay, now we're good. Now we use the zero product property, which I was delighted to see at least one person doing in class. She said, well, if this product is 0, then the factors must separately potentially equal 0. In other words, one of them has to equal 0. So either cotangent of x is 0 or cosine squared x minus 2 is 0. Okay, so we have two equations we got to solve. Now this one over here is this equation is what we were talking about a couple of minutes ago. This is what we would have been left with had we simply divided out cotangent. So this is part of the story. What you find is when you take a square root of both sides and you try to solve in this, we get plus or minus the square root of 2. Well, square root of 2, this is plus or minus approximately 1.41. And 1.41 is greater than the maximum value in the range of cosine, right? Cosine only goes from -1 to +1 and never outside of that. So both of these values are outside of that. 1.41 is too big, -1.41 is too low. So from this branch of our solving here, from this part, we get no solution. And if we are disappointed by that, then we should be happy to know that we have another equation to solve over here. So cotangent of x is 0. All right. I saw somebody, maybe it was the same person, do this. In other words, since cotangent is cosine over sine, and this is 0, well, then the only way this can be true is if the numerator is 0, right? Sine can't have anything to do with it. Certainly sine of x cannot equal 0 for this to come out to 0. And with sine of x equal to anything else, cosine would have to be 0. So this is what this really comes down to. Cosine of x has to be 0 for cotangent of x to be 0. And so therefore, we look at our unit circle, and I might as well just draw one out here. Let's make a unit circle. Okay, let's see. All right. And good enough. Okay, so what were we? Got to remember, cosine of x is 0. Okay, so where do we have a cosine of 0? X equals 0 right here on the y-axis. So we have a cosine of 0 at this point and at this point. So that's pi over 2 and 3 pi over 2. And you'll notice, this is a fact that we're about to use, you'll notice that for me, if let's say I start at pi over 2 and I want to take a step to get to the next one, that step would just be pi radians. Well, you get the idea. If I add pi radians, I go around to here, 3 pi over 2. If I add another pi radians, I get up to 5 pi over 2, and that's coterminal with 1 pi over 2, right? The point is, if I keep adding 1 pi, I will go from here, down to here, up to here, down to here, and I'll just keep alternating back and forth. And in so doing, if I do that, you know, if I basically, well, I'll write it out a little bit more exactly, but as I'm doing that, what I'm getting is this complete set of all angles that are coterminal with both natural solutions, pi over 2 and 3 pi over 2, both positions. So here's what all that does for me. I can write down here, x is pi over 2 plus pi k, with k any integer. There it is. Okay. So now this is done. So let's just look one more time. What happened? We got we factored it. We got a 0 on one side. We factored it. This factor yielded no solutions. This factor, when equal to 0, yields all these solutions. When x equals pi over 2, we have a cotangent of 0. When x equals anything coterminal with pi over 2, we have a cotangent of 0. Furthermore, if we add an odd multiple of pi, so if we add 1 pi or 3 pi or 5 pi or negative 1 pi or negative 3 pi or negative 5 pi, any of those will get us to the bottom of the unit circle, coterminal with 3 pi over 2. Cotangent of that angle also is 0. So all of these are solutions. Okay, moving on. This one, okay, so the piece of advice I had for this was that you should try squaring both sides. Okay. Now this one's going to get a little crazy because something strange is going to happen when we square both sides, and we won't see what that is really until the end. And we had a pretty good discussion about this in one of the sections of pre-cal, but we didn't get to it in the other sections. So here we go. Let's square both sides. Be very careful. I would say 9 out of 10 students at this point, or at least 9 out of 10 of my students, ouch, that was mean. Sorry, guys. Let's put it this way. 9 out of 10 of the students today in my class were making this mistake, and you know what? Probably even more of the students outside of my class make this mistake. Yeah, how do you like that? Okay, here's the mistake people were making. They were squaring these terms individually. In other words, they were saying, if I square the left side, it should be cosine squared x plus 1 squared. Well, that's not how you square a binomial. You square a binomial like this. Binomial times binomial. Like that. Well, I squared that side. But here, I'm going to square this by doing first, outer, inner, last. So I get cosine squared x plus cosine x plus cosine x. So that's 2 cosine x. I'm not going to show every step because there's a lot to talk about here. I mean, really. Plus 1 times 1. Okay, and then bring down the other term. Now, this is quadratic, but I have to deal with this. And it's not the same unknown. This is cosine of x. This is sine of x. What do? I use the Pythagorean identity. I use sine squared plus cosine squared equals 1, right? Which means sine squared equals 1 minus cosine squared. Okay, so I have cosine squared. I'm bringing everything down. 2. I had one student do like a boatload of this in his head today, and it kind of amazed me. This can be replaced by this, and then if we want to solve this as a quadratic, you guys know what to do. We need a 0 on one side. So we're going to add cosine squared to both sides. We're going to take 1 away from both sides, subtract it. So we have, when we add cosine squared, that's 0, and this becomes 2 cosine squared. When we subtract 1, this becomes 0, and so does this. So then we only have to bring down this, and the other side is 0, which is what we want. Okay, now we don't have to use the quadratic formula here, Because we have a common, we only have two terms, and they have a common factor of cosine, right? Cosine's a factor in here, cosine's a factor in here. So let's bring that out. Cosine of x times this plus this equals 0, right? This product equals this. Now we can do the same thing that we did right here. We had a product that was equal to 0. We split it into 2. We solved. Same thing, right? 0 product property. Cosine is 0, or 2 cosine plus 2 is 0. Okay, so that means, now we already did this one, right? Cosine is 0. Leads to, yeah, we were right here, leads to this. So we know what that's going to be. Okay, so we'll get to that in a minute. This one, if we subtract and divide, we have cosine is -1. Okay, so where is a cosine equal to -1? Well, that's only at the bottom of the circle. No, sorry, not the bottom of the circle. What am I saying? What's wrong with you? Over here, this is where the cosine is -1. And that is pi radians. And of course, it would be pi plus 2 pi k. So we have both. We have the solutions from over here, which are pi over 2 plus pi k. And we have the solutions from over here, which are pi plus 2 pi k. Okay. So I told you earlier that this was a little weirder. This is where it's going to get weirder. So let me just pause for a second. Okay, so here we are. This is what I did with one of my classes, which was to show the two sides of this equation. We've got cosine x plus 1 equal to sine x. So we graphed cosine x plus 1 and we graphed sine. And look at what happens. We have two curves, and where they intersect, those are the solutions. So this is our solution set right here, right, that we should keep an eye on while we look at this graph. And we see pi over 2 plus pi k, so there's your pi over 2. And if you add pi onto that, you get 3 pi over 2. Do I see that? No, I don't. That doesn't seem to be a solution. Well, let's just make sure we have some of these others first. Pi is a solution, I see that. Pi plus 2 pi is 3 pi. He's over here. Pi minus 2 pi is negative pi. I see that right here. So I appear to have pi and 3 pi and negative pi and negative 3 pi. So this one seems to be working out. But something's going wrong with this one, right? We don't have 3 pi over 2, right? We have pi over 2. We don't have 3 pi over 2. But then we do have 5 pi over 2. And we don't have, and if I were to subtract pi, I don't have negative pi over 2, that's down here, but I do have the next one, negative 3 pi over 2. So it seems to be skipping. It seems like we're getting every other one. Okay, now here's what we should say about this first of all. We, up here, did a handy thing, which was to square both sides. And that was handy because it allowed us to do all this. It allowed us to get a sine squared, so we could replace it with 1 minus cosine squared, put everything in terms of one unknown, solve it like a quadratic, or solve it like a, with the zero product property. Great. Except that what we did here was kind of the opposite. It was the opposite problem from what happened here. Remember here when we said, hey, you know what? We really don't want to just divide these out because then we're dropping some of the solutions. Well, okay. What happens if we square it though? If we square it, we pick up some solutions that aren't supposed to be there. So when we go ahead and solve, we don't leave out any solutions. Contained within this set are all the solutions, but also we have what are called extraneous solutions. So somewhere lurking in here, and we know exactly where because we looked at the graph, we have extraneous solutions. Okay, so, and we see which ones they are. So in order to determine which ones they are, we're going to have to break this one apart into its constituents. We have pi over 2 we have 3 pi over 2, and let's just throw this one as well. We have pi. In other words, what appears to be the solutions to these two, cosine is either 0 or cosine is -1. If we look at the unit circle and we say, what angles make cosine either 0 or -1? We have 3. 1, 2, 3. So it looks like as far as angles go between 0 and 2 pi, these are the 3 that solve our equation. These are the 3, right? And any other solutions would have to be coterminal with these 3. Now what that also means is that if there are any extraneous solutions, which we know there are, that means one of these has to be extraneous, and we can just eliminate it right now. Well, we can see from the graph which one that is, right? We got pi over 2, that's an intersection point, that's a solution. We got pi, that's an intersection point. But 3 pi over 2 is not a place where cosine of an angle plus 1 is equal to the sine of the angle. Right, okay. So, therefore, this one is out. And we would simply carry these two with us and say I have pi over 2 plus 2 pi k, right? Only full revolutions. Adding on only angles coterminal with pi over 2, not angles coterminal with 3 pi over 2. And also angles coterminal with 1 pi. Those also are solutions. So this one, this set, and this set for all integers k. Okay, now we still got a little ways to go in this video. That one took longer, I think, than the others are going to take. Okay. All right, so here we go, continuing on. All right, now I suggested that you use sum and difference formulas. Okay, so those are going to come into play in this problem. Okay, so sum and difference formula. What is it? Okay, the sum and difference formula that's relevant here is this. When we have the sum or the difference of two parts within the argument of sine, right? Here's how you handle it. You're going to have the sine of one argument times the cosine of the other, plus or minus the cosine of the first argument times the sine of the other. So you see, in both cases, it's just cosine times sine, but we swap the arguments. Here, sine gets the alpha, here cosine gets the alpha. And if we're adding here, then we're adding here. And if we're subtracting here, we're subtracting here. And that's the way the identity goes. So that's going to be handy here because we can break this, which is made up of two parts that we can't combine because they're not like terms. We can take this and break it into all of this here. So this is what we're going to do. We're going to do this part right here. We're just going to do one piece at a time. Okay? This part is sine x times the cosine of pi over 4, that's a pi over 4, plus, since this is a plus, cosine of x times sine pi over 4. So all this comes from this right here. Now we're going to do this. So let's bring down our addition operator. And we've got the sine of, so it starts the same way. Cosine of pi over 4. Okay, but now since I have a subtraction operator, I'm going to use the subtraction operator, and I'm going to use it here. So I've got cosine of x sine pi over 4 equals -1. Now you see how nice this is? I can already start eliminating stuff. Okay, so this is equal to this, and it's gone. And now I have, from these two, I have 2 sine x. Now you know what? I'll do it next. 2 sine x cosine pi over 4 equals -1. Cosine of pi over 4, I know what that is. That's root 2 over 2. So I have root 2 over 2, this is square root of 2 over 2, times 2, gives me just the square root of 2. So I have square root of 2 times sine equals -1. I divide. And now it's really going to help to rationalize the denominator. If you guys remember what that is, it's really going to help to do this because look what happens. That's something I can deal with. I know where that happens. We have a sine of -√2/2. We have a sine of -√2/2 in two places. That is, whatchamacallit, what is that? 5 pi over 4. And this one here, whoop. Okay, so all the way around is 7 pi over 4. Yes. Okay. So these are the two angles that are between 0 and 2 pi and solve my equation. So I'm going to say x is this one and this one. And then I add to get the full set of coterminal solutions. Okay, now one more. My goodness, it should not shock you that we are now going to use the double angle, the last one. With our last ounce of strength, we cross this off the list and use a double angle identity to solve this, which means we're going to use the identity that this right here is equal to 2 sine x cosine x, and bring down the rest. So 2 cosine x plus 2 sine x cosine x equals 0. Well, if you were paying attention for, and I know you were, for this one and for this one, I think, yes, at this stage of the game, then you'll probably have some idea what we need to do, you'll probably have some idea what we need to do here, and that is to factor out the factors that these two terms clearly have in common, which 2 cosine x, that's what it is. If we take it, we can take it out of both. And then use the zero product property. 2 cosine x can be 0, and so can 1 plus the sine of x. Yeah, all right. So then we divide by 2, and we have cosine x is 0, and by God, we've already written out the solution set for that twice, so you know what it is. And where is the sine of x equal to -1? Funny story, that's one of the places where cosine is equal to 0, right? Cosine is 0 here and here, and this is where sine is equal to -1. So it looks like we just need all of the angles that are coterminal with these two positions, and that just comes down to pi over 2 plus pi k. And in this case, I can very conveniently avoid 2 pi and just write 1 pi, because if I add multiples of pi, it's going to walk me between these two, right? This plus pi is this, and this plus pi takes me back here, and this plus pi takes me back here, etc. So we finally have the last solution set.